Okay, thank you. I haven't wrote much yet. So a definite integral is in the form of integral with from a to b of f of x dx, where a and the b are constants. So this integral with the lower and the upper bound, we call this a definite integral. As when we evaluate this integral, we always end up with a number. So a definite integral gives a number at the end. So that's a definite integral. An indefinite integral, which we have seen last semester when you took calculus 1. It's basically the antiderivative. So an indefinite integral, sometimes called antiderivative. So that is integral from just, we don't have lower and upper bound of f of x dx. So that's the indefinite integral. If we evaluate this, we should get a function, right? It's not a number, we should get a function. And I'm going to use capital F of x to show that's a function. Indefinite integral is a function. But if you remember that when we find the antiderivative, that's always a constant c with get the c there. So that's the difference. How are they related? They are related in a way such that if we were to evaluate the definite integral using the antiderivative, we get f of b minus f of a, where capital F of x is antiderivative of lowercase f of x. So even if you work with definite integrals, you still end up finding the antiderivative first, and then you're going to plug in the a, the b to evaluate the difference. So whether you're working with definite or indefinite integrals, you always can end up finding the antiderivative, whether it's in the process or as a final result. All right, so that's just the difference between those two integrals. I always, every time I see indefinite integrals, I think about antiderivatives because they're really the same. And in the book, in section 5.4 on page 410, there's a table of common integrals that people use a lot in calculus. I'm just going to write down a few here. All right. So there was a few we already talked about before. So if we integrate a constant times a function with respect to x, you remember that we can pull out the constant and then just integrate the function with respect to x. That will give us some function, right? And if we're integrating x to the n dx, we remember that using the reverse of the power rule in differentiation. So we're just going to end up adding 1 to the exponent, so x to the n plus 1, and then divide by the new exponent. But don't forget there's a c there. So I should use like a capital, this is a capital C, that's a constant. And the integral of e to the x dx, that give us just itself, e to the x, but don't forget to add a capital C for the constant. and the integral of 1 over x dx, that gives us natural log of absolute value of x plus a constant. So whenever you work with indefinite integrals, there's always this constant. The first one I didn't write it, but if we were to evaluate this, so there's also a constant c there. Different from the constant coefficient, it's just another constant c after we evaluate the integral. And last time we saw that if we integrate a raised to the x dx, so if the base is not an e, it's a, different from the e to the power of x. So this one, we should get a to the x, just like we get e to the x from integrating e to the x. But because of the base is not e, so we have an extra part, which is a natural log of a in the denominator. Right, we saw that last time. What else? And then there's a sine. Oh yeah, we saw the sine and cosine, so I'm going to use this part. So if we're integrating sine x dx, we end up with negative cosine x dx. Sorry, just negative cosine x plus a constant c. I forgot a c here. If we're integrating cosine x dx, we end up just positive sine x plus a constant c. And we also saw this last time, 1 over x squared plus 1 dx. That gave us inverse tangent of x plus a constant. You don't need to copy down those basic integrals, but it's very important that you look at them. It's actually very helpful if you try to memorize them. I'm not going to give you a quiz on that, but for your own benefit, you might want to memorize them. And there's integrating secant square x dx that give you tangent of x plus a c. Right. So that's a lot of this. And in fact, let me get the textbook. So I want to show you, I don't know if you have a paper copy with you. So if you look into the textbook, the front of the textbook, the front page, you cannot see because I'm, I get it. Hold on, let me change the background, realize that. All right, anyway, so if you look into the front, there's like a tape formulas, right? Basic formulas you learn in geometry. But then if you look into the back of the book, so the back from page 6, the reference page 6, so you have all the integral formulas there. So if you ever forget something, you can always go to the back of the book and look for the integral formula that you need. So that's a lot of them. It's like a 4 pages or 5 pages of them. But most of them you probably never need it. But just in case you forget some of this, you can always go to the back of the textbook and find it. Any calculus textbook you use, you can always find like a few pages of formulas for integrals. All right, like I said, this is on page 410. There's a table there. You can take a look and try to memorize the basic integrals there, because you're going to use a lot in this class and also future classes. All right, so with that said, I'm just going to give you a couple examples. It's not really new material. We could have done this in calculus 1 or last time, but I just want to kind of use them as a review. So for example, the first one, we want to integrate this fraction with respect to x, right? It's a little bit difficult because we have this numerator has 2 terms, the denominator has 1 term, But when you see a problem like this, you might want to simplify, right? Put into two fractions. So you can rewrite this function as the first part is just 2x squared square root of x over x. You can simplify the x in the numerator and denominator. And then the second part is just 1 over x, which is nice because we know how to integrate 1 over x dx. Right? So the first term, if we simplify the x, we get 2x square root of x. After we simplify, we get 2x square root of x. Again, you can rewrite x square root of x as x times x to the half. So that's x to the 1 plus half in the exponent. That's x to the 3 half. That's the first part. And then the second part is just, it's better just to leave it as 1 over x. This is 2x to the 3 half dx minus integral of 1 over x dx. And then the first part, we can use the power rule. So bring the 2 outside. So 2 integral of x to the 3 half dx minus integral 1 over x dx. That gives us 2 times x to the 3 half plus 1, right? We have to add 1 to the exponent and divide by the new exponent. So that's a 3 half plus 1, that's a 5 half. But then we have to divide by 5 half from the whatever we have. And then minus the integral of 1 over x, that's just natural log of absolute value of x. But don't forget to add a c at the end. So one more step just to simplify the 2 over 5 half. That's a 2 over 5 times 2. That's a 4 over 5 x to the 5 half minus natural log of x plus a constant c. This is the antiderivative. That's what we get when we evaluate the indefinite integral. This is a function, it's not a number, right? Oh, how is it 3 half? I erased it. So what I did is I took this part after I simplify the x from numerator and denominator. I get 2x square root of x, right? And I leave the 2 alone. I didn't even touch the 2, so I'm only working with the x square root of x. So that will give me x to the first power times x to the half. This is indefinite integral, yes. Thank you. And then when you multiply 2 terms with the same base, you add the exponents together. So you get x to the 1 plus 1 half in the exponent. And that will give you x to the 3 half. That's where the 3 half come from. Good question. Any other questions about this problem? All right, the next example I have, it looks difficult, right? Because you have cosine in the numerator, then you have sine square, then you have sine square in the denominator. We're integrating this. There's a couple ways. One is that we can rewrite this. So I'm going to rewrite the fraction as just splitting the sine square. So that becomes integral of cosine theta over sine theta, and then times 1 over sine theta. So basically just splitting the square as the product of 2 terms, that's the same. Theta, and then we're just going to rewrite each of the terms. So if you recall that cosine over sine is cotangent, right? So we get cotangent theta, and the times 1 over sine, that's cosecant theta, d theta. So basically we're integrating cotangent times cosecant. And if you recall, or if you have the textbook already, you can look into the table. So we call that derivative of cosecant, derivative of, cosecant theta or cosecant x is equal to negative cosecant x cotangent x. But here we have a positive that we're integrating. So we basically end up moving the negative sign to the left side so that we have a positive cosecant cotangent term. So we're basically saying, okay, if we differentiate negative cosecant x, we should get positive cosecant x cotangent x. Now, if we integrate it, so we're doing the opposite process, we should get negative cosecant x. So let me write this, maybe help, maybe not. So if we integrate with respect to x on both sides, you can think about the integral with respect to x and the differentiating with respect to x, they cancel out. So the left side, we just have negative cosecant x. The right side, we still have this integral. The integration undoes the differentiation. I just want to show you that. So we just have negative cosecant x plus a constant. So 1 and 2 are examples of indefinite integrals because we don't have lower and upper bound that we can plug in. So we end up with functions. And it depends on what C is, we end up with slightly different functions. The next example, 3, if you just look at it, it's a little bit different because here we have lower bound is 1, the upper bound is 2, right? So now this is actually a definite integral. We should end up with a number, not a function. So I'm going to have to integrate this, but the first thing is that we take this function, we need to find the antiderivative. Okay, so we basically need to integrate each part separately. So I'm going to use slightly different notation we did last time. So I'm just going to separate this integral as integrating from 1 to 2 of 3x squared plus 1 with respect to x, plus integrating from 1 to 2 cosecant square x dx. And the 3 from the first term, I'm going to move it outside of the integral. So I get 3 integrating equal from 1 to 2, 1 over x squared dx plus 1 dx, moving the 3 to the outside, to the left side of the integral, plus integrating 1 to 2 cosecant square x dx. Now the next step is that just assuming we don't have the lower and the upper bound, right? We need to find the antiderivative. What is the antiderivative of 1 over x squared plus 1? If you recall that we did it last time or just from what I wrote. So if we're integrating 1 over x squared plus 1, we get inverse tangent, right? Arctan, exactly. Yeah. As Aiden said, it's arctan. That's good. So I'm going to just leave the 3, but I have inverse tangent or arctan of x. But this function, this is the antiderivative, right? We need to evaluate this from 1 to 2. So I'm going to put a vertical line there. It means I'm going to evaluate this part. The 3 doesn't matter. You don't have to keep the 3 when you plug in value. You can just put the 3 outside. So I'm going to evaluate this from 1 to 2. Plus the next part, cosecant square x. If you look it up, it's cotangent x, but it's negative. So that's a negative cotangent x. When we differentiate it, we get cosecant square x, or if you integrate cosecant square x, you get negative cotangent x. And then after this is the antiderivative, but we still have to evaluate this function we got, this part, from 1 to 2. So that's a key there. You always remember after you find the antiderivative, you need to plug in numbers to evaluate it. So I'm going to write the next step, which is 3. I'm going to add a bracket because I need to plug in 2 first and then I'm plugging 1. The 3, I can put it outside. So I get inverse tan of 2 minus inverse tan of 1. That's using the FTC2 we talked about last time. And then plus a negative. So here the negative sign you can also pull out. You don't have to keep the negative sign for each term when you plug in 2 and a 1. So you can just write negative and then just plug in 2 into cotangent. 2 and then put 1 there. You could keep the negative with the cotangent, it's up to you. So here I don't have a calculator, so I'm going to leave it with a calculator, or if you use trigonometry, you can simplify this a bit. But and no matter what, at the end you should end up with a number. So the result is a number. How are you guys doing on this? Any questions about those examples? So I just want to use those 3 examples as a review. Any questions before we move? Or I'll stop. I see some of you still writing down the questions. It'd be positive cotangent 1. Because Ryan, I think you're right, but the way I wrote is that I kind of factored out the negative 1. So the negative 1 the negative sign I did not carry with cotangent. So you can write this as negative cotangent of 2 minus negative cotangent of 1. So that will give you a positive cotangent of 1. I think that's what you meant. So either notation is fine. Okay. I'm not hearing any questions. Can we move on? All right, if you need a little bit more time to finish writing the notes, let me know. All right, I'm going to move on. The next part is called net change theorem. It's actually it's really not that you actually have used this already in examples. So let me just copy down the net change theorem from the book. So the net change theorem says the integral from the book as well. The integral of a rate of change is the net change. So what that says is that so if we're integrating from a to b of f prime of x dx, where f prime, so this part is the rate of change of some variable. And then we write f of b minus f of a. So this expression on the right side is a net change of some variable. Here's a couple examples. So let's just see the net growth rate, the growth rate of some population. So suppose growth rate. So here, this growth rate including birth rate and the death rate altogether. So the growth rate of some population, of a population, is, let's just see, let's see, I'm going to use M. I'm going to use R for growth rate, R of T, right? So that's R of T is some function, depends on time. That's the growth rate. And if I want net change, so if I integrating R of T from T1 to T2, this stands for time of R of T dt. So this gives net change in total population from year T1 to year T2. That's what that expression says. So here R of T is the growth rate. It could be 5% of the population every year, and the T1 is the beginning year, and the T2 is the final year. If you want to know how much did the population increase or decrease, the net change will be given by this integral. Another example, suppose that we have water that goes into a tank. Suppose water flows into a tank at a rate W of T. It depends on time again. So if we're integrating from T1 to T2 of W of T with respect to T, we're integrating the rate of change of water. So water goes into a tank at a rate, so that's the rate of change of water. So if we integrate that between two times, we get the change of volume of water from T1 to T2. So that just the total amount of water going into the tank. So that gives amount of water goes in the tank. From T1 to T2. So that's what that integrals give you. The integral give you. I'm going to go over one more, then I'm going to skip the marginal cost one. So the next one is called change of position. So suppose some object has velocity v of t, right? And if you recall that if we integrate velocity, we get the position function, the distance function, actually not the distance, the position more precisely. So if we integrate velocity function from T1 to T2 with respect to T, we get a position function. So this gives us the net change in position from t1 to t2. Now, I want to point out that this is a term that you have to be very careful. So when we see net change in position, it means displacement. It may or may not be the same as distance. So this is not necessarily the same as distance. I'm going to use one example to show you why they're not the same. Because if we have if you think about, if we have a particle that, let's see, moves up, and then moves down, and then moves up, right? It's going up and down, up and down. So the total distance covered is not the same thing as the net change in position, right? Because if you assume that the particle begins here and then end up here, after a certain time, the change in position is actually zero. It's not moving up and down if you just look at the net change in position. But the distance it covered, it's not zero, right? It goes up, so that covers some distance, goes down, covers some distance. So the distance is not the same as displacement. So just be careful with that. I'm going to use one example to hopefully clarify that part. So here's one example. If you don't feel like you have to copy down the question, this worksheet is available to you on the website. So the question says, the acceleration function of some particle that's moving along a line. So here's the line, and then there's a particle that's moving in some either left or right. I don't know, but it's moving along that line, but it's staying horizontally. And we know that the acceleration is given by 2t plus 3. That's what we know. And then we know that the starting velocity is -4. So let's just see, this is the time equals 0. And the -4 just means to the left. So here we're taking positive directions going right. So -4 means going left. And then we want to know the velocity of the particle at time t. Well, hopefully you remember that to get velocity, so velocity is equal to the integral of acceleration with respect to time. Just like a position is the integral of velocity with respect to time. So from here, we're just going to integrate the acceleration function. So that's equal to the integral of 2t plus 3 dt. And then just work out each part. So the first part, integrating 2t, just like integrating 2x. So that gives us x squared. Here's t squared. And then the second term, the 3, when we integrate it, we get 3t. And then there's one more term, right? Because this integral we work with is not a definite integral, so we have a c constant. I believe that at the end of calculus 1, you kind of cover some of this material. So that velocity tells you how the particle moves. But this is not this is not the velocity function, right? Because we have a c we don't know. We have to use the information given. It says initial velocity is -4. So use initial velocity. Actually, I'm going to use V0, stands for initial velocity, is equal to -4 to find C. And doing the work quickly, so we get V of t, plug in 0 there, so V of 0 equals -4, so that's equal to 0 squared plus 3 times 0 plus C. So C equals -4. Don't forget to put back into the velocity function. So V of t is equal to t squared plus 3t minus 4. Any questions about finding the velocity there? Okay, the next part is we want to know the displacement of the particle. So the displacement, like I said earlier, that is equal to the net change in position, right? So to find displacement, that's equal to net change in position. And then using the net change theorem, so that's equal to the definite integral from t equals 0 to t equals 3 of the rate of change. The rate of change of position is lost. So I said that just now that when we look for the displacement of some object moving, right, that is always equal to the net change of position, the net change of the position function. And that is equal to the definite integral from A to B of some rate of change function. The rate of change of position is the velocity. So we're basically integrating the velocity function from 0 to 3 with respect to t. So this is what the net change theorem says. If you want to find the net change in something, you have to integrate the rate of change of that variable. In this case, the velocity is the rate of change. So velocity is rate of change of position. So displacement is equal to definite integral from 0 to 3 of the velocity function which we found just now. So that's a t squared plus 3t minus 4. We're going to integrate that with respect to time. That will give us a net change in position, which is displacement. And I'm just going to integrate each term separately. So integrating the first term, t squared dt, that will give me, I'm going to be a little bit lazy here, not writing that step. So t squared give me t cubed over 3, right? If you recall that. Add 1 to the exponent, divide by the new coefficient. But we need to evaluate this from 0 to 3. You can evaluate later. You don't have to evaluate this now. And then the middle term give me t squared, but then I have to divide by 2, so that's 3 over 2t squared from the middle term. And then the next term is negative 4. So that's a negative 4t. And there's a c here, but we remember we don't need to add a c when we evaluate definite integrals. And we're going to take this expression, this function, we're going to evaluate it from 0 to 3. So plug in 3 in there, and then I'm plugging 0. Obviously, when you plug in 0, you can see everything becomes a 0. So really just end up plugging 3. So we get 3 cubed over 3 plus 3 times 3 squared over 2 minus 4 times 3. I believe you get 9 here, plus the middle term give you 27 over 2, then you minus 12. That's a number. That's a 13.5. You get 10.5. Excellent. Thank you, Daniel. That's good. So you get 10.5. That's a displacement, right? That's like, after 3 seconds, from 0 to 3, the difference is 10.5 meters. if we keep the unit there. So that's the displacement. So t equals 0 is here, and then t equals 3. You end up there. So the distance is 10.5. So that's finding the displacement. You're basically integrating in the given in the given interval. But then the last part says, so that's one more part. It says find the distance traveled during that time, the total distance. So you have to be very careful here when you try to find the distance traveled, because the particle begins from this at t equals 0, it begins with a negative full velocity going to the left, right? But perhaps at some point, it's going to go to the left and then turn around, go to right. So it doesn't always go in the left direction. So you have to consider how far it goes to the left and how far it goes to the right. So let me draw another diagram to find the total distance. So let me add more space here. So C, to find distance. So when we find the distance, we have to include all the distance. So perhaps the particle goes from, at the beginning, t equals 0, it goes left, and then it turns around to go right. Right? So, and then it stops here. So we need to take both parts, both distance, add them together. That's what we need to do. And then you have to figure out where does it stop. We need to know when does this stop happen. Like what's the time when it stopped, when it changes the direction to go to the opposite direction, right? So we need to know this point. Well, one thing to keep in mind that whenever a particle going in one direction and then turns around to the other direction, that's where the velocity equals 0. So this point, velocity equals 0 at this point right here. So that's the information we're going to use. That will give us how long it takes to get there and then turn to the opposite direction. So what do we have? We had the velocity. So recall that velocity equals t squared plus 3t minus 4. So we need to know when it becomes 0. So we set v equals 0. So that's t squared plus 3t minus 4 equals 0. I'm going to factor this. So that's a t plus 4, t minus 1, negative 4, positive 3t minus t. Yeah. And then that will give us t equals 1 and a t equals negative 4. But we're not working with a negative time. Time is always positive when we talk about distance velocity. So drop the negative time. So this point happens when t equals 1. It's 1. So that's what we found. Right? So now we need to find the distance. We need to find the distance from t equals 0 to t equals 1. And then we need to find the distance from t equals 1 to t equals t stop, which is 3. Which is given, right? We're looking at the distance from 0 to 3 seconds. So find the first part, the distance from 0 to 1. So we're integrating from 0 to 1 of the velocity function, t squared plus 3t minus 4 dt. And the second part, we're going to integrate from 1 to 3 of the same function, t squared plus 3t minus 4 dt. So that will give us the two distance separately. So the first distance, since I already did the antiderivative earlier, so I'm just going to copy the antiderivative here. So that's a t cubed over 3 plus 3t squared over 2 plus minus 4t. that's going to go from 0 to 1. So just end up plugging 1 there. So you get 1/3 plus 3/2 minus 4. I'm not sure what that number is. If someone can help me, that'll be great with the calculator. So that's a 1.5, negative 2.5 minus 0.3, about negative. That's negative 2.167. Suppose. And then the other direction, the distance covered by the blue segment I have in the diagram. We're going to do the same thing. We're going to take this t cubed over 3 plus 3t squared over 2 minus 4t, evaluate it from 1 to 3. So you take 3, put in there. We have done that before. We get 10.5. And then we're going to minus the number we get, which is negative 2.167. Sorry, I did it too quickly. Maybe I should write it down. So that's equal to plug in 3. So 3 cubed over 3 plus 3 times 3 squared over 2 minus 4 times 3. That's plug in the first number, the upper bound. And I'm going to subtract the value I get when I plug in the lower bound, 1. So that's 1/3 plus 3/2 minus 4. And then this number, it gives me 10.5 minus a negative. So that's equal to 10.5 minus a negative 2.167. And that's actually 12.667. If you no, you don't have to. You can. That's a great question. Feel free to use whatever you found already. You use it directly. That's perfectly fine. Because it's really the same process, right? So how do we find the total distance? It goes to the left side by 2.167 units, and then it turns around goes to the right side by about 12.6 units. Well, total distance, you have to include all of them, right? Not just like, it's not just the difference between them. You have to include all of them. So the negative, the first negative means just going left. The positive means going right. So if you want to find the distance, you have to take the absolute value of each one of them and add them together. That's the key part. Because you only take the magnitude, adding them together, not the number itself. That's an absolute value sign. So that will be the total distance, which is, yeah, I'm not going to do the calculation. It's about 14 something. I just want to use this example to show you that when you find the distance, especially when you look at problem like a particle moving along a line, it doesn't tell you if it's going to keep in one direction. Very likely the particle is going to switch directions in the process, right? So you have to be careful there. Or if you have something that that going up and down in that motion, like if you have an object you're throwing up, then it's coming downwards. So the displacement is not the same thing as distance traveled. So be careful with those two terms. This is a good question. There's a few exercises in the book that you can look into if you want more practice. Any questions on this problem? I know it's very long. I just want to cover both displacement and the distance to show you the difference and not the same. Displacement is either you integrate it using the the beginning and the end time, and that whatever the number you get is the number, right? But distance is not. You have to take the absolute value of each part of the path and add them together. And I throw in the first part, just just a practice to finding the to find the indefinite integral. Any questions? Because if you don't have questions, I'm going to move on to the next section. But do we need to take a break? If we don't take a break, I'm going to finish at 7:50. Just how do you? Oh, okay, that's a good question. How do you know it tends at t equals 1? So this is so one thing I know is that let's just see. Let me just draw another diagram here. Let's just see. We're assuming that there's a particle or some object that moving horizontally, like along that line. So let's see if it go. We're going to assuming that going right is a positive direction. So let's see if it starts going left. That means it's going to have a negative velocity, right? But if it goes right, if at some point it tends in the right direction, so if it goes right, it's going to have a positive velocity. And in the middle, when it goes from a negative velocity to a positive velocity, it has to pass a 0 velocity. So the velocity has to be 0 in that middle when it goes from negative to positive. That's why. So that's why we set the velocity equals 0 to find t equals 1. Good question. All right, so Aiden is good to keep going. Anyone else? Okay, 2, 3. All right, excellent. All right, let's keep going. I'm going to finish before like 7:50. Just so that I got some time. All right, so the next part is the substitution rule. It's, if you recall, it's actually when we take the derivative, we have a chain rule that we use, right? So if we take the derivative of, I forget what the notation was, like f of g of x, and we take the derivative of the outer function first, but keep the g there, and then we're going to take the derivative of the inner function, right? So that's the chain rule. The substitution rule is sort of similar to that, but it's for integration. It's not for differentiation. But before we talk about the rule, let's just look at a few examples I give. So number 1, if we want to find the integral, can anyone tell me what we should do first? So if we want to integrate x times x squared minus 5, what do we do first? Just the first step, you don't need to tell me the final answer. Simplify, right? So you might want to simplify. The best way here is just distribute the x in there. So you're integrating x cubed minus 5x dx. You can integrate each part separately. So I'm not going to do it. I just want to write down this to show you. You can find the integral easily. Okay. Now, what about the second example? It's x times x squared minus 5 squared. Can we do the same thing? No. Right, you cannot distribute directly, right? So you cannot distribute the x into the parentheses directly, but we could simplify this term by expanding it and then distribute the x in there. So that becomes integral x times, I'm going to do it quickly, so that's x to the 4th minus 10x squared plus 25. And then you can put the x in there, so you end up with 3 terms, x to the 5th minus 10x cubed plus 25x. You can integrate each term separately from there. There's no big deal, right? But then, well, what if we end up with 100 power, right? A 2 is easy, you can expand it. A cube, yeah, you can expand it, take a little bit longer. But if you have a power that's that's a lot larger, then it's not practical, right? Exactly. So can't really simplify there. So this approach doesn't work. So we need a new approach. So need a new approach. Same thing with if you have a square root, you just, if you can bring x inside by putting as x squared. So you can write as square root of x squared times x squared minus 5. And you can simplify the part underneath the square root as x to the 4th minus 5x squared dx. But then you cannot integrate directly. You cannot just say, oh, that's a square root of whatever the antiderivative of each term. So we get, so cannot integrate further using the technique we know. So this is a case that we need a new rule. It's called the substitution rule because we use u for substitution a lot. We sometimes call it u-substitution, but anyway, just a substitution rule. So here's what it says. Let me copy down some notes. And then I'm going to walk you through the process of applying it. So if we want to integrate f of g of x and then g prime of x, I'm going to explain what that is, dx. So if we try to integrate something that this part is the derivative of the inner function. So g is the inner function of some function f, and the g prime, this is the derivative, or looks like it's derivative. So I should put quotation, not necessarily, doesn't have to be exactly the derivative, it has to be, never mind. Derivative of inner function. If we have this structure, if you integrate some function f, inside you have another function, and the outside is being multiplied by the derivative of that inner function. If you have this structure you want to integrate, so we can let u equals g, and then du will be equal, so g of x, so du will be g prime of x dx using chain rule. So this part we had, it just becomes using this part, so this integral becomes integral f of u now if we substitute g of x with u, and then we substitute g prime of x dx with du, so we end up with this. So that just becomes f of u. But this is what the u substitution really says. It probably doesn't make much sense to you, but I have a few examples that I prepared. I'm going to go through them with you. Perhaps it will make it easier to apply the rule. But the rule generally is saying that if you look at the structure, if it looks like it's a product, and then one part of the product is one part of the product like this is the derivative of the inner function. If you have that structure there, then you can always use this u substitution. Okay, so let me try with the first example. May not be the best example, but why don't I just take an example I had earlier? So let me take the example. So let me use the example. So use example. What's the example I'm going to use? I'm going to use number 4. Integral of x square root of x squared minus 5 dx. So I'm going to use that example to show you the steps. So the first step, I'm just looking at, just by inspection, looking at the function given. I see a product, I see x times something. So I have this part, then I have the square root. And it also looks like every time I have a square root, so I have an inner function. So this looks like an inner function to me. Right? And then the x looks like the derivative of the inner function. Looks similar, that is not exactly the derivative, right? So at least because I had a lot of experience, so it looks like the x is a derivative of the inner function. So it's sort of fitting in the structure that the substitution rule says. So what do we do? So the first step, so step one, we're going to let u equals inner function. So here, I'm going to let u equals x squared minus 5. And then I'm going to say du, take the derivative on both sides. Du, take the derivative of 2x, that's of x squared, that's a 2x, and then dx. And with the derivative of negative 5, it becomes a 0. So we don't have to write the 0 there, just 2x dx. Right? So that's what the du is. And the step two, so we let u equals the inner function, find du. That's all in one step. The next step is that we're going to solve for dx. This is what I do. So, if you've seen this before, you probably try something different. But for me, I like to solve for dx. I'm going to solve for dx from the derivative. So divide by 2x, so that's a 1 over 2x du. That's what dx is. How do we know when to use the u substitution? That's a great question. So generally speaking, I just look at the function given. If I see a product, right, one term and another term multiply together, and then one of the term seems to be the derivative of some sort of inner function of the other part, that's sort of the indication to use substitution. Or sometimes you look at it, it's like, oh, I see something a little bit more complicated. But if you can identify a inner function, you can always try the u substitution. It may not work, right? But at least try it. It might work after you use substitution. Exactly the same thing. So you got du over 2x. It's the same thing as 1 over 2x times du. So now the next step, after I solve for dx, I also have u. So step 3, I'm going to use substitution. So substitute for the inner function using u. And also we're going to substitute dx with whatever we have. So substitution, so the integral we have becomes, so the integral x square root of x squared minus 5 dx, that becomes integral, the x is still there, but the square root of x squared minus 5, that becomes square root of u. And then the dx becomes a 1 over 2x du. That's really nice because if you notice here, so we have an x here, and then we have 1 over x, right? The x in the denominator. So if we multiply those together, the x will go away, which is good. So we end up with integrating square root of u, and then we have a 1/2, but I always put the constant outside. So I'm going to put 1/2 in front. Square root of u du. So as you can see, now the integral we have just have u. It doesn't have x in it, just u du. That's it. It doesn't have any function of x in there. Now we can integrate this directly. So that will become 1/2. This is integrating u to the 1/2 du, just like we integrate x to the half dx. So that will become 1/2 u to the 1/2 plus 1 is 3/2. And then we have to divide by 3/2 plus the c. So if you rewrite that a bit, so that becomes 1/2 divided by 3/2, that's times 2/3. So they get 1/3 u to the 3/2 plus the c. So step 4, I didn't write down the step. So we just integrate, so evaluate the integral. So that's what I did from here to here, just integrating that function, square root of u du. Now, the last step is just substitution again. Because we begin with a function x, we want to end up with a function of x, not a u. So the very last step, just go back to replace a u with whatever we set u to be. So that's a 1/3 x squared minus 5 to the 3/2 plus a c. That's the very last step. So would the u substitution be the indefinite integral? So for now, we work with indefinite integral. For definite integral, it's the same. It's that's two approaches. One, you can do the same thing, just at the end plug in the two numbers, the lower and the upper bound. There's another approach that's slightly different. So we're going to talk about that next time, perhaps. So for definite integral, you could evaluate it at this step by finding the correct u, or you could evaluate at this step by plugging the x value directly, which we will talk about next time. But any questions about this process, about substitution? You basically have to, you have to take whatever you have, right? You have to write it so that you end up with the integral of u and the du. And then you integrate that, but at the end, you have to go back to substitution to get a function of x. But the key is that you always set u equals some kind of inner function that will help you with the integral, turn it into an integral of u. All right, I'm not seeing any questions, so I'm going to move on. All right, I'm not going to do example 5 I picked because that's basically the same thing as the example I went through. I just have a -2, so you can just split the integral into two integrals, work on each part separately. So the second two doesn't really matter. I'm going to work on example number 6, which we're integrating e to the 5x dx. That's an exponent, 5x. So here, I'm just by looking at it, I don't have like a product, right? I only have one term. So I can assuming that that looks like there might be a integer that, like an integer times this. So if that's the case, so I'm just looking at the structure, it looks like to me that this is the inner function. And then that function, if we find the derivative, it should be a constant. So similar to, so that derivative looks similar, not exactly, to this constant 1 we had. So it's still sort of fit in that structure. Right? If you don't see that, that's okay. So you just let u equals the inner function 5x, and then use change rule du equals 5 dx, and then solve for dx. So dx equals 1 over 5 du, or du over 5. And then I'm going to take the u and take the dx and the 5x. I'm going to use substitution there. So this integral becomes integrating e raised to the u now, and the dx is 1 over 5 du. And then the 1/5 can go to the front. So I got 1 over 5 integrating e to the u du. And I'm pretty sure that you all know what e to the u is when you integrate it. So just get 1 over 5 e to the u plus the c. And don't forget one more step to substitute for the u there. So you got 1 over 5 e to the u is 5x plus a c. So this example is a lot easier. Any questions about 6? All right, I'm not seeing questions about 6. So I'm going to move on to 7. All right, so 7 here. So I have 4x, and then multiply with secant squared. Okay, I'll go back up a bit. All right, I'm going to post this notes on Canvas after this lecture. So if you miss some parts of it, don't worry too much about it. All right, number 7. So here we have 4x multiplied with secant squared, and I'm just looking at it. So obviously the second part, this part looks like it has the inner function, which is this is part. So that looks like the inner function. And just by looking at it, if we take the derivative of the inner function, we should have some number times x. So that looks like the derivative, or similar to the derivative. Right? So that means I'm going to try the same trick. So I'm going to let u equals the inner function 100 minus 5x squared, and the du, which when we take the derivative of 100, we get 0, but the negative 5 stays. The x squared give me 2 times x, and then dx. So if we simplify this a bit more, so that's a negative 10x dx, right? And that's actually pretty good because in the original integral, I got 4x, and I also had a dx. So it looks like the same type expression. So I'm going to solve for dx. So dx equals 1 over, so negative 1 over 10x du. So now I'm going to take the u, use it to substitute for the inner function. I'm going to take dx, put back into the integral. So I have integrating 4x stays, and then secant squared of u now, that's the inner function u. And the dx becomes negative 1 over 10x du. This is, again, just like we had before, right? If you have an x in front of it, and then you have an x in the denominator, so when you multiply those together, the x go away. And then the 4 and then the negative 1/10 becomes negative 4/10. So that's the integral negative 4 over 10 secant square u du. Again, right now we end up with the integral of just u and the du, right? Which is good. So I can pull out the constant because I don't want to work with it. So that's negative 4 over 10 or 2 over 5. secant square u du. And if you remember that when you integrate secant squared, you get tangent. You get negative 2/5 tangent u. That's a constant c. And then we almost there, we just have to make sure that at the end we end up with a function of x, not u. That's negative 2/5 tangent u is 100 minus 5x squared. So in the future, when you have problems like this, you look at it, you don't know how to, you look at it, none of the rules that you learned in the past apply, right? Try substitution, identify the inner function, set it with u, and see if it helps. It may or may not help you, but at least try it. A lot of time it's just kind of guess and check, but the more examples you work with, the easier it gets, the easier to identify which rule to use. And the next example, I'm not going to fully solve it just to save some time. But if you just look at it, sine x times e to the cosine x, right? So here, by just looking at it, every time you have an exponential function, you might want to consider setting the exponent to be the inner function. That's just kind of a trick. So this should be the inner function. So you're going to let u equals cosine x. So du is equal to the derivative of cosine, which is negative sine x dx. And to solve for dx, we get dx equals 1 over negative 1 over sine x du. And if we put it back into the integral here, so we're integrating sine x times e to the u, and the dx becomes negative 1 over sine x du. So as you can see, just like before, now we have sine x will be canceled with the sine x in the denominator. So we just end up with negative integral e to the u du. And then we can continue and finish it. But I hopefully, at this point, you are pretty comfortable with integrating e to the u or e to the x. But I just want to start this problem to show you what to do. Any questions about 6, 7, 8? No? Okay, good. Let me know if you have questions. The next one is the same. So number 9. Again, so even though the structure looks complicated, right? You get a cube root as the denominator, you get x squared in the numerator, then in the cube root, you still get something. And it doesn't look like a product, but keep in mind that quotients are basically products that are the same. So I'm just looking at it. Looks like to me that I have two parts. The x squared is one part, and then the cube root seems to be a different part, right? And then also the 5 minus x cubed, if we take the derivative, looks like we're going to end up with some square. So let's try use substitution. So let u equals, obviously inside the cubic root, that's the inner function. So I'm going to let u equals 5 minus x cubed. And then du, just like we did before, use the chain rule. So that's a negative 3x squared dx. And then we're going to solve for dx. That's a negative 1 over 3x squared du. So I'm going to put into the integral. So the integral becomes x squared divided by cube root of u now, just u, nothing else. And the dx becomes -1/3x squared du. It's really nice because again, the square and then the square in the denominator, they cancel. We just end up with -1/3 integral of 1/cube root of u du. And I hope you recognize at this point, you can actually find the antiderivative by rewriting the cubic root as u to the -1/3. So that's -1/3. That's a constant coefficient we had. But then the integrating u to the -1/3. The -1 is because it's in the denominator. The 1/3 is because it's a cubic root du. And then you can follow the tricks that we did before to integrate this. Questions? I really want to go through number 10 because that's an example that's a little bit different from what we have seen before. Because if you look at number 10 here, I just want to put it side by side with number 9 so you can compare it. So number 10, remember I said earlier, you have to kind of have to look at it, see if you have a derivative, you know, one part is a derivative of the other part, right? So here, if you look at it, if we call this is the inner function, right? But this is not the derivative. X cubed is not a derivative of x squared, right? And also, if you kind of going the other way, if you say, oh, what if we call this the inner function? Is x squared minus 1 the derivative? No, it's also not the derivative. So it looks like it doesn't fall in that pattern that we have used before. The trick here is that actually the x cubed is actually, you can write as x squared times x. So that the x is a derivative of the x squared minus 1. So this part, this x alone is a derivative. But the x squared, then we have to rewrite it using u. That's the trick. So nevertheless, let's try use the substitution. So let's call this the inner function. So we're going to let u, just assuming that it works, let u equals x squared minus 1. And then du equals 2x dx, just like we have done before. And then from here, we can solve for dx, which is 1/2x du. And I'm going to go back to the integral, do the substitution like we have done before. So that becomes integrating x cubed times square root of u. Dx becomes 1/2x du. So that becomes, so I'm going to take out 1x from x cubed to cancel with the x in the denominator. So I get integral of x squared square root of u, and then 1/2. 1/2 I'm going to put it in front of the integral always, and the du. So we almost get what we wanted, right? Except for the x squared. So this is not good. So not a good term. Because we cannot integrate directly with x and the u all in there. We're going to do something. So the trick is that we have to rewrite. So need to rewrite x squared as function of u, some function of u. That's what we need to do. But it doesn't mean that the integration by substitution, right? Doesn't mean the substitution rule we did is wrong. X squared. Exactly. You could do that too. Aiden, that's a good point. Yeah, at the beginning you could use that substitution directly, but I didn't. I just used the normal way. It's okay. We can still get there, right? So we need to write x squared as a function of u. And from we're letting u equals x squared minus 1. So from u equals x squared minus 1, we know that x squared is equal to u plus 1. Right? Yeah. So we're going to use this part to substitute for x squared. So that becomes 1/2 integral of u plus 1 square root of u du. Oh, so what I did is that, so for number 10, so I follow the normal substitution process, right? I set u equals x squared minus 1, I found the dx, and then I substitute into the equation, and I end up with this expression, right? That's what I get by using the normal process. But the problem is that I have an x squared, which is the extra. I don't like x squared to be in that integral. I cannot integrate there. So what I did is that I need to replace x squared with some function of u, some expression with u. So from the beginning, we said, okay, we're going to let u equals x squared minus 1. And I can solve for x squared from there, right? So if we do that, so this, what I did is coming from the beginning, right here. So from there, we can solve for x squared, and then x squared is equal to u plus 1, like Aiden said, and then we can take u plus 1, put it into the integral to replace x squared. So now we just have, we have an integral with only u there, which is great. So that's just 1/2 integrating this part. If you don't know how to integrate it, you can always distribute the square root of u. And then you get two separate parts. So that's a u to the 1 times u square root of u. That's a u to the 3/2. This is a u to the 1/2. I'm just distributing it into the parentheses. Plus u to the 1/2 du. And then I'm going to stop here because I assume that you know how to integrate each term separately. Right, so the next step, just take each term, add 1 to the exponent, divide by the new exponent, and you should be able to end up with a function of u. Don't forget to substitute for x at the very end, for u at the end. So this is a good example. So if you end up with some function, you just by looking at it directly, you feel like it doesn't take you anywhere. Just try it. Try the substitution method, and it may or may not simplify. It depends on the question, right? So if it does, great. If it doesn't, well, just try to look around, find other approach. So I didn't finish this problem. If you're interested, you can finish it, but I think the rest should be manageable. All right, here's the next question for you. If we want to integrate tangent theta, what's the integral of tangent? If you without looking up on the internet, we don't know, right? We know how to take the derivative of tangent, but we haven't integrating tangent before, right? But if you rewrite tangent as sine and cosine, it's actually a lot easier. So if you rewrite this as sine theta over cosine theta, d theta, looks like it doesn't help you, but actually it does, because if you say, okay, I'm going to let u equals cosine and the derivative, so that's sort of the derivatives of each other, right? That's a benefit. So here we can see we're going to let u equals cosine theta, and the du will be, well, when we take the derivative of cosine, we get a negative. So we get negative sine theta d theta. And then I can solve for d theta there. So d theta is equal to negative 1 over sine theta du, just like we would do normally. And then I'm going to take this, rewrite the integral. So that becomes integral sine theta over u times d theta, which is negative 1 over sine theta du. And the good thing is that sine and the sine theta goes away in this process. Just end up with u left. So we get negative integral of 1 over u du. And if you recall that one of the common integrals, it just integral of 1 over u or 1 over x give us natural log. So we get natural log. That is a great question. What happened when we set u equals sine, so du equals cosine? It's sort of from experience. You generally want to set u, if you just have like a numerator and denominator, there's no straightforward in and outer function. It's always good to set the denominator to be u. That's sort of just the experience I had. So if you don't know which part to set to be u, it's always good. You can always try to set denominator or part of the denominator. Exactly. So set part of denominator to be u. That's sort of the what I found to be helpful from my experience. But anyway, so that's a natural log of u, absolute value of u, and the plus a c, and don't forget to rewrite u there, which is cosine theta. Yes, the negative you can always put it out. Just like if you have like a constant, so you can always put a constant out. I always do that because I don't like to have constants inside integrals because they don't get involved in the process. So just put it out. All right. On that note, I think it's a good time to